Unit Operation Classroom, an initiative of unitoperation.com. Um, we are discussing now GATE 2023 question 34, and my name is Shekhar Bhattacharjee. A liquid L containing a dissolved gas S is stripped in a counter current operation using a pure carrier gas V. So this is we'll discuss more about the absorption and stripping operation in the next slides. But basically, what is happening here? So this is a liquid L coming from the top of the tower here, and this contains let's say a pollutant or a contaminant, and its concentration is mole fraction is 0.1, and it has to be the concentration has to come down to 0.01, so it's around 10%, is around 1%. That's my target. Okay. And the equilibrium distribution of S between V and L is given by Y is equal to XC. So basically, in each of these stages here, so there's a liquid coming from the top, and there's a gas, which is, so this is the gas entry coming from the bottom. And what happens, equilibrium is established, and let's say this is my XC, the mole fraction of the contaminant or the solute in the liquid phase, and YA is the mole fraction of contaminant in the vapor phase here, and there's an equilibrium, and according to the relationship given, Y is equal to XC. That is given. Okay, the molar feed rate of the carrier gas stream is twice as that of the liquid stream. So basically, what we have here, so this is my gas stream, which has no contaminant at all. In fact, that's what is meant here, using a pure carrier gas V. So Yn plus 1 is equal to 0, and this is going out to reach and let's say its mole fraction is Y1, and the ratio of the carrier gas stream is twice that molar feed rate is twice that of the liquid stream. So V is equal to twice L. Okay. We have to find out the minimum number of ideal stages that will achieve this reduction in concentration. So we are going to use Kremser equation. Again, we will discuss that a little details in the next slides. And of course, this is the equation. We know the value of x0. We know the value of xn, and yn plus 1, of course, is equal to 0. So these terms are 0. And the value of a, which is the absorption factor, is L over mv. L over v is given, and m is equal to 1 here. So y is equal to xc. So absorption factor is equal to half. And if we do the calculation, n becomes equal to 2.46. So we need 3 stages to achieve this reduction in concentration. Okay. So that is the answer. 3 stages is the answer. So you can stop the video here if you want to, but there are some additional informations given in the next slides. And also, I must insist that always read a very good internationally accepted textbook to clear your concepts. These videos, these are just an aid, and they are not, you should not really depend entirely on them. So let's go to some absorption and stripping operations. These are, of course, extremely important and very widely practiced unit operations in the chemical process industries, in refineries, natural gas processing, petrochemical complexes, and the syngas and hydrogen plants, ammonia plants, where ammonia, of course, let's say in the urea nitric acid, and the ammonia from the purge gas, and that is stripped with water. Sulfur dioxide in sulfuric acid plants, smelters, the power plants, flue gas desulfurization. We use water, hydrochloric acid, chloralkali plants. Of course, they come out, and the PVC plants. So, so these are the absorptions operations here. And what is an absorption operation? Let's quickly see what the solutes, common solutes and the solvents, and then we'll just briefly see what is an absorption operation. I'm sure you already know. For carbon dioxide, we use MEA, DE, and MDEA, where MEA is, just a second, MEA is monoethanol amine, and DE is a diethanol amine, and MD is usually methyl diethanol amine. And these are, of course, the structures given here. So what happens, let's say if this happens, it is MEA and DE, they readily absorb carbon dioxide and H2S. So let's say this is the flue gas coming in containing, let's say, the carbon dioxide, the sulfur dioxide, etc., or carbon dioxide, H2S, etc. And so what happens is, we put the lean amine, so that assuming there is no concentration of CO2 or H2S in it, so there is a counter current operation, and there's this contacting in each stage between the liquid and the gas, and there's a transfer of these, let's say, carbon dioxide from the gas phase to the gas phase from this gas phase to the liquid phase, which is coming in. So this liquid comes rich in carbon dioxide, and the carbon dioxide, or the H2S, and the lean gas, which has a much less concentration of carbon dioxide, let's say, compared to what is coming in, goes out, and depending upon the concentration, it can be discharged to the environment or further treatment. So these are typically absorptions. So for carbon dioxide, as we said, we use these. For sulfur dioxide, we use normally water or alkalis, sodium hydroxide, calcium hydroxide, ammonia solution in, like, in the fertilizer or the power plants. For ammonia in the gas phase here, we use water, readily soluble, sulfuric acid, of course, reactive absorption, nitric acid, hydrochloric acid, etc. Okay, so these are common examples of absorption. Uh, what are the common examples of stripping in refinery, ammonia, urea plants? Again, an extensively used unit operation. Petrochemical complexes in the power plant for boiler feed water treatment, for stripping of oxygen from the water, and the regeneration of solvents for environmental applications, where there is a tandem of absorption and regeneration columns. I'm not going to go into details of that. Let us quickly see what are the examples. Let's say if carbon dioxide, say in the cooling water on the condensates, we use air and steam. These are the normally stripping gases we use. Sometimes nitrogen is used in pharmaceutical industries. H2S, which comes out from the refinery, sour water strippers, effluent treatment plants, we use the same. Sulfur dioxide comes out from sulfuric acid plants, and the smelters. So these are the water containing these pollutants. We use air stream for stripping. In ammonia comes out from municipal or industrial ETPs, pharmaceutical companies, electronics industries again. BTES, benzene, toluene, ethylene, xylene. Of course, removal, extensive treatments are used for groundwater treatment in the refineries. Okay. And as we say, let's say this is a typical sour water in a stripper. This is a typical sour water coming in, and we put steam or air through it. And there is, of course, a transfer of these pollutants from here to the steam in on each stages. And what happens is that the treated water which comes in has much less concentration of these pollutants, and this has a much higher concentration. That's what it's giving. So that's what is stripping operation. For application of the Kramsar equation, which we have used to find out the solution of our problem, following are the conditions that must be satisfied. Number one, counter current staged operation, just like this, liquid and the vapor coming in from the counter current directions. Dilute solution has to be a dilute solution, so that we have a constant L and V, constant molar flow rates of the liquid and the vapor. Linear equilibrium relationship. The equilibrium relationship has to be linear. If it is something like this, of course, you will not get good results. Constant molar flow rate, which of course is true only if it's a dilute solution. Either absorption or stripping with ideal stages. So whether it's absorption or stripping, you can use the Kramsar equation. Why it is important? The Kramsar equation is the early design stage. Okay, just to see what will be the minimum number of trees, maybe for the costing purpose or on the initial feasibility stage, and what is the effect of steam and the air flow rate on the total number in the operations. Okay. Um, we'll quickly see the summary of Kremser equations. These are separate for absorption and stripping. First, we will see absorption. As we said, absorption is transfer of solid from the vapor to the liquid phase. That is absorption. So let's say you have a gas for whose concentration, inlet concentration is already known, and let's say you have the value of the solvent which is used. We have seen examples of several solvents, and let's say this x0 is equal to 0. That means this solvent does not have any solute to start with. Okay, so if we know the number of stages, if that is already known to you, you can calculate the value of y1. That means what is the value of or the mole fraction that the solute has in the effluent gas. Okay, exiting gas from the countercurrent operation system. When pure solvent is used, which is normally true, but again, this is not a requirement. It can have a positive value, but normally we use pure solvent. In that case, this is the equation which we use. So these equations are used for just to prediction of what would be the, let's say, the mole fractions here. But these equations and we know the and this is the equilibrium relationship we already know. Now the same equation can be written in a different form, because let's say yeah, we know the value of y1 plus 1, we know the value of y1, and we know the value of x0, but we want to see how many number of stages is required. Okay, here in these equations we already know the number of stages required, we want to find out this one. But if it is the other way, if you want to know yn plus 1, if already yn plus 1 is known to you, that means inlet mole fraction, and what is your target mole fraction, that means how much you want to reduce the concentration, and you want to know how many number of stages required, then the same equations can be written in a different form, which is this one right here. Okay, and here as you can see, for a is equal to 1, this equation breaks down. So for a is equal to 1, you use this equation here. So that's for absorption. So we have similar equations for stripping, the same Kremser equation. In stripping operation, we know the concentration of the pollutant or the contaminant or the solute in the inlet liquid, and we want to let's say it's being stripped with let's say air or steam. Normally the concentration of the solute here is equal to 0, but it can be any positive value, and you want to know what is the value of xn. That means at what concentration is coming out. You already know the value of number of stages, so this is already known, and for a certain liquid and the vapor fluid, and the equilibrium relationship y is equal to mx. Okay, so this is the same equation. This is the equation which we are going to use, and this is the absorption factor, and the stripping factor is just the inverse of that. And this equation, same equation, can be written in terms of the stripping factor. And just as in case of absorption, let's say if you already know, if you know the value, you already know, of course, the value of x0, and you have a target xn, and you know the value of yn plus 1, as I said, this is normally equal to 0, and you want to find out how many number of stages. So the same equation can be written in a different form. Here, this equation is if yn plus 1 is equal to 0. If this is equal to 0, then this equation here this equation is rewritten in the form of this equation, where of course yn plus 1 is equal to 0. As I said, if you want to find out the number of stages, then this is the equation here. Again, this is in terms of absorption factor, and this is in terms of stripping. And as I said, if S is equal to 1, then what we have here, we use this particular equation, but normally we do not encounter this one here. So if this is for S not equal to 1, or A is not equal to 1. Okay, so this is just a summary of Kremser equations, and these are the examples of absorption and stripping solvents and the operation here. So the answer to this one is 3 stages. So that's the answer.